right. In the beginning of chapter 15, we talked about kind of our umbrella effect of thermodynamics. And the first thing we said we were going to talk about was the heat transferred in and out of the system and talk about enthalpy. So that's what we've been talking about, basically. So last class, we went over Hess's law, how we can determine delta H of a reaction based on the heats of formation. And those are the values that are in the back of your textbook, right? Okay, so we took the summation of heats of formation of products minus reactants. And there you go. You could find or estimate what your delta H would be for a reaction. So that was one of the main things that we did last class. We talked some about energy, and that was the end of class. And our delta E and delta H for most times in chemical reactions are the same. Okay, and that's because pressure and volume doesn't change very much in a chemical reaction. We're usually trying to keep those constant. And so delta E and delta H, don't let those confuse you. Number 10 on that homework has that. So are usually the same unless I otherwise specify that they're not. The second part of that kind of umbrella is being able to predict whether a reaction is going to be spontaneous. Okay, what do you think about anybody in here spontaneous? Don't we have somebody, didn't you break your arm doing something? Was that you? Okay, so you're spontaneous. What does that mean? You just do it, right? You just go, you don't think about the end results, you just do it, right? So that's what spontaneous means. Okay, a reaction's very similar to that. If it's spontaneous, it's just going to do the reaction on its own. There doesn't really have to be anything else put into it. It's going to occur on its own. Okay, so we're going to try to predict whether or not a process will occur under certain conditions and whether or not it'll be spontaneous or non-spontaneous. Okay? Typically, we want a reaction to be spontaneous, right? If you think about it, that's kind of in your favor in the lab. Okay, you don't have to sit there and do all sorts of different tweaking of conditions and doing all kinds of things if it'll react on its own, right? Okay, so that's kind of what we are trying to get to in a lab. Okay, if your product, okay, when you run a reaction in the lab, what you're wanting to happen, and you've done this in the lab, you want your product to be made efficiently in the most highest yield possible, right? So when you made aspirin, your goal was to first make pure aspirin, okay? And second was to make it efficiently, okay, to make the product, okay, in the best % yield that you could. Okay, and so if your product is more stable, okay, meaning lower in energy. So y'all remember our exothermic kind of diagram we looked at a while ago? Remember the products were lower in energy, right? Okay. This is said to be thermodynamically stable. Remember, thermodynamics is energy, it's heat. Okay, and that's what we were looking at in an energy diagram. Okay. If it's stable, that means it's spontaneous or it's product favored, right? We want to make the products spontaneously, so just think of it that way. And that means the product is lower in energy than the reactants. Let me think backwards here. So here's your reactants. We had an activation barrier, and then here are the products. Okay, lower in energy than reactants. Okay, if the product is less stable, I'll do this, okay, then it's going to be non-spontaneous, meaning it's reactant favored, okay, because it's going to go this way instead of this way, okay. And the reactant is lower in energy than the products. Okay, one thing to remember, okay, and I'll say this a couple times today, is in chapter 15, we are looking at stability. Okay, we're talking about spontaneous, will a reaction occur, and even occur even on its own. Okay, it does not tell you how fast the reaction will be. Okay. Chapter 16, what we'll do next week, is kinetics. That's how fast it's going to occur. This is not telling us anything about how fast it will occur. Okay, diamond, this is an example of this, it will, over millions of years, spontaneously decompose to graphite. Okay, good thing it doesn't happen, or men, you'd be buying a lot of rings. Okay, it doesn't happen quick. Okay, so over millions of years, it does it on its own. We don't have to put anything into it. It does it on its own, but it is extremely slow. Okay, so you get what I'm saying? It doesn't mean it's fast because it's spontaneous. Everybody wants to kind of think fast, spontaneous. It just means it will occur, okay, on its own. Okay, but it may be fast or it may be slow.
So if you do something to speed it up, it's no longer spontaneous?
Do what now?
If you do something to speed it up, and it's taking away the spontaneous?
Not necessarily. It depends on, we'll talk about the different variables that you can change temperature, and that could speed it up and also make it spontaneous. Okay, but you could heat the reaction, but for that particular reaction, it actually makes it non-spontaneous. Okay, so the temperature can vary. Okay. A spontaneous change, like we said, it happens without any continuing outside influence. Okay, it has a natural tendency or direction. Okay, so example would be rusting of iron. It's going to go in that direction. So iron's going to rust, oxidize, but you don't see it doing it in reverse on its own, do you? Okay, we have to work hard or do a lot of things to try to get rust off of iron, right? It's not going to, your rusted chair on your back patio, like I know I have, is not going to just one day, I'm not going to walk out there and it be gone. Okay, it's going to be spontaneous in the direction of the rust. Okay, the same thing for melting of ice. So if we take ice out of the freezer or it falls on the floor or whatever, then it's going to melt at room temperature. However, when it's sitting there on the floor, it's not going to go back to being frozen, right? Unless you put it back and change the temperature and you put it back in the freezer. Okay, so looking at these two, these are the diagrams we looked at earlier in the chapter, so quite a bit earlier, last week, I guess. Okay, looking at these, here's an exothermic reaction. There's our activation energy. Here's our products. And then we have an endothermic reaction. This was just, I believe, melting of the ice or whatever. So which one looks to you, after what we've explained, which one looks like it would be spontaneous? Which one? Which one did you say? Okay. That's a good point. So how much energy you need, that's going to come into play more with our kinetics, okay? How fast, how much does it take to get over? But with our stability, that's what we're looking at. Which one's products are more stable? That's what we're looking at, okay? So more stable equals lower in energy, okay? So it looks to me that these are lower in energy than the reactant. So when that ball goes to the top of the hill and you let it go, what's it going to do? It's going to go. Exactly. So up here, okay, your products are higher in energy. So to me, it looks like the reverse would be more likely. Okay. So by looking at these, I would think, okay, exothermic would be spontaneous. Bless you. Okay, but actually, yes, exothermic reactions can be spontaneous, and there are more exothermic reactions that are spontaneous than there are endothermic reactions. Okay, but both can be spontaneous. Okay, so that means that there's got to be other variables involved, not just delta H. Okay, which is pretty much what we're looking at here. Okay, we're looking at that heat evolved, this delta H. Okay. So I'm going to try to show two videos real quick. And one is an exothermic spontaneous reaction, and one's an endothermic. That way you see both of them. And the sound may not work at first, so I'll just bear with me because I'm tied into the recorder right now. Something real quick. just gonna. Well, I can pull this recorder out, but it's going to stop the recording. I'm trying to just get it to switch to computer sound. Here we go. Oh, never mind. No, I don't want you. I want you. Here, wait. Computers downstairs just automatically send it out to the classroom. Let me see if I can just turn this